Are we truly alone? Tales-ByEve. For as long as we've looked up, we've wondered, are we really alone? Beyond our pale blue dot, across the vast silence of space, lies a question so ancient. It echoes in every culture, every civilization, every soul that ever dared to dream of the stars. And yet silence. No greetings, no signs, no cosmic postcard saying, you're not alone. But what if the silence isn't silence at all? What if someone or something is trying to reach us, and we're simply not listening the right way? From radio telescopes scanning the heavens, to engineered messages riding light years of emptiness, humanity has been whispering into the void, hoping to hear a whisper back. This is the story of our search, of signals, probabilities, paradoxes, and hopes. From the brilliant minds behind the Drake equation to the haunting silence of the Fermi paradox. From government-funded observatories to private initiatives breaking through the cosmic static. And, at the center of it all, a question that could change everything we know about existence. Welcome to Tales-ByEve. I'm Eve, and this is not just science. It's a conversation with the universe. Are we truly alone? The search for extraterrestrial intelligence. Tales-ByEve.
Welcome to the Deep Dive. Today, we're taking a plunge into how we listen to the universe's whispers, bounce our own signals off cosmic neighbors, and, well, search for signals that might hint at other intelligence out there.
That's right. It's a deep dive into radio astronomy, radar astronomy, and the search for extraterrestrial intelligence, or SETI. And our map for this journey comes primarily from excerpts of a handbook by the International Telecommunication Union, the ITU, along with some related texts.
Okay, let's unpack this a bit. The ITU, that's the global body usually sorting out things like, your phone signal or TV broadcasts. Why are they involved with telescopes?
Well, because the radio spectrum, that whole range of electromagnetic waves we use for communication, it's a shared resource, and it's finite. Radio astronomy relies on receiving these incredibly faint natural radio signals from space, which happen to use some of the same frequencies.
Ah, I see. Competition.
Exactly. So our mission here is to understand the science behind these cosmic observations and searches, and crucially, why protecting specific parts of that radio spectrum is just absolutely vital.
All right, let's start where the sources do. What exactly is radio astronomy?
Simply put, it's astronomy based on receiving radio waves from cosmic sources. I mean, we're used to seeing the universe in visible light, right? But radio waves reveal a completely different picture, showing us things that are otherwise invisible.
Like what kind of invisible things? What are we talking about here?
Well, for starters, fundamental physics and cosmology. A classic example is the emission from neutral atomic hydrogen that's the most common element in the universe. It emits radio waves at a very specific frequency, 1420 megahertz.
1420 megahertz. Okay, why is that frequency so important? Seems specific.
Because it's essentially the universe's baseline frequency. By mapping this hydrogen, astronomers reconstructed the structure of our own Milky Way galaxy. They even found its center, which is totally hidden by dust in visible light. It's like mapping the skeletal structure of the universe.
Wow, mapping the basic stuff. Okay. What else can radio waves show us?
Oh, lots. The cosmic microwave background radiation, the CMB, this faint glow, it's the afterglow of the Big Bang itself.
The actual Big Bang.
The echo of it, yeah. Studying its tiny temperature fluctuations across the sky, they look like these little splotches in the diagrams, has been hugely significant. It helped us understand the universe's geometry and, crucially, confirmed its accelerating expansion. The measurement of these precise variations even earned a Nobel Prize back in 2006. That's a major point from the source's direct proof of the Big Bang, seen in radio waves.
That's mind-blowing that we can pick that up, just faint waves.
Absolutely. Radio waves also let us peer into regions of intense star formation that are hidden by dust, or observe something called synchrotron radiation from powerful radio galaxies. Plus, radio astronomy can achieve the highest angular resolution of pretty much any astronomy technique.
Higher resolution, meaning sharper pictures.
Exactly, and incredibly precise measurements of object positions and velocities.
You mentioned measuring velocities. Is that where those spectral lines come in again? We touched on that.
Precisely. Spectral lines are like unique radio fingerprints left by specific atoms and molecules out in space. They emit or absorb radio waves at very, very particular frequencies.
Fingerprints, okay.
And yes, by measuring their Doppler shift, how these frequencies are shifted slightly depending on whether the source is moving towards or away from us, we can figure out not just composition, but also its motion and distance.
So the shift tells you speed and direction, like a cosmic radar gun.
Sort of, yeah. The 1420 megahertz hydrogen line's Doppler shift, for example, reveals how galaxies rotate. Another incredible example is water masers. They emit super bright lines at 22.235 gigahertz, so strong they can be used to measure distances directly, even to other galaxies. The sources mention there are thousands of detectable spectral lines out there.
Thousands of cosmic fingerprints floating around. What kinds of objects are leaving these fingerprints or blasting out radio waves?
Oh, a fascinating variety. Pulsars, for instance. These are rapidly spinning neutron stars. Their discovery back in 1967 was kind of serendipitous, actually, and led to a Nobel Prize in '74.
Right, the spinning stars.
Yeah, and they pulse with extreme regularity. They act as cosmic clocks, so precise they're used to test fundamental physics, search for gravitational waves, and they even led to the first exoplanet discovery back in 1992.
Cosmic clocks and exoplanet finders. That's a surprising dual role.
It really is. We also study things like magnetars, neutron stars with magnetic fields trillions of times stronger than the sun's, and we analyze the faint cosmic background noise itself. It all tells a story.
So how do we actually listen to all this cosmic radio chatter? What are the tools, like big dishes?
Well, the fundamental tool is a radio telescope, which is essentially a large antenna and a very sensitive receiver. The simplest is a single-dish telescope. You point it at a source, measure the signal, then you measure points around it like the A, B, C, D points around source S, shown in one of the figures to subtract the background noise.
Got it. So you isolate the signal from the general cosmic hum, the background static.
Right. But to get really sharp images and high resolution, astronomers use interferometry. This combines signals from multiple antennas spread out over distances, sometimes even across continents or into space, with something called space VLBI.
How does spreading them out help with resolution? It seems kind of counterintuitive. More antennas, sure, but spreading them out.
Think of it like having two eyes. The wider apart your eyes are, the better your depth perception, right? Interferometry essentially uses the distance between the antennas as a baseline. By combining the signals and accounting for the tiny time differences they arrive, astronomers can synthesize an image with a resolution of a single telescope as large as the distance between the furthest antennas.
Whoa, okay, so the distance becomes the size of the telescope, virtually.
In terms of resolution, yes. Modern techniques use really sophisticated digital processing to handle the immense data volume. You see this principle in action in stunning images like the radio view of the supernova remnant Cassiopeia A.
Okay, using distance for resolution that clicks. So that covers the science. But the sources, coming from this ITU handbook, they spend a lot of time on the practical value. How does this pure radio astronomy research actually benefit us here on Earth?
Right, and this is where one of the core takeaways of this deep dive lies. Fundamental research, even seemingly abstract work like listening to distant galaxies, is a powerful driver of practical innovation. Radio astronomy has led to numerous technologies we now totally take for granted.
Okay, give me some examples. What everyday tech came from listening to the stars? I'm curious now.
Telecommunications, for one. The need for extremely sensitive receivers to pick up those faint cosmic signals led directly to the development of low-noise amplifiers. Those are now standard in satellite communication dishes, like the one you might have for TV.
No kidding, my TV dish.
Yep. And antenna design improved drastically. Features like circularly polarized feed horns developed for radio telescopes were adopted by satellites. Even the engineering principle called homology, developed back in '67 to design giant parabolic dishes that maintain their precise shape under gravity, that's used in large antennas everywhere today.
So, better satellite TV dishes, thanks to space science. That's a really tangible link.
Exactly. And the sheer volume of data radio telescopes pushed the boundaries of computing. The need for faster automated data processing led to improvements in parallel computing methods and even the development of a specific programming language, Forth, at the National Radio Astronomy Observatory.
Data processing advancements make sense. That volume must be huge. What else?
Signal processing. The algorithms developed to extract those weak cosmic signals from noisy data found applications in other fields entirely. They're used for analyzing faint signals from X-ray sources in medical imaging, and even in early skin cancer detection, helping spot tiny color variations characteristic of malignant melanoma.
Wait, hang on. Detecting cancer, how does that link work?
It's the technique spotting subtle signals or patterns in noisy data. And the imaging techniques themselves, the ways we process radio data to create pictures, were foundational to the development of X-ray diagnostics and computerized tomography, your CT scans.
You're telling me listening to the universe helped invent CT scans? That's pretty incredible. What a spin-off.
Yes, the data processing methods are remarkably similar. It's also used in geophysics, analyzing seismometer data to find oil or mineral deposits. So looking way out at the stars really does help us look inside the human body and under the ground. It's amazing.
Yeah, that's a powerful argument for funding basic science. Wow. And the sources also highlight something called solar radio monitoring. What's that about?
Right. This is a specialized area focused specifically on observing the sun's radio emissions. It's crucial for space weather research.
Space weather? Like cosmic rain forecasts. What does that mean?
Not quite rain. Space weather forecasting provides critical, timely alerts about solar eruptive events, things like solar flares and coronal mass ejections, CMEs. These events blast charged particles towards Earth, and that can have a significant societal impact.
How so? What kind of impact?
Well, they can disrupt or even damage our technical infrastructure. Satellites, aviation communications, power grids, even pipelines can experience accelerated corrosion. A famous example is the 1989 Quebec blackout. It was caused by a geomagnetic storm kicked off by the sun.
I remember hearing about that big outage.
Huge. That single event resulted in something like $1 billion loss and knocked out power for over 9 hours. Solar radio monitoring is an automatic, relatively inexpensive way to get consistent data on these events, and it has a history going back over 60 years.
Protecting the power grid, helping with CT scans, improving satellite communications, all stemming from trying to understand the universe's radio signals. But, as we established with the ITU's involvement, this all relies on access to the radio spectrum, right? And that spectrum is getting clouded.
That is the core challenge, and honestly, it's kind of existential for radio astronomy. The ITUR manages international frequency allocation. Radio astronomy is classified as a radio communication service, and crucially, it's almost entirely passive. It only receives.
And that's the problem, being passive.
Yes, because the cosmic signals are incredibly weak. We're talking orders of magnitude, tens of decibels, weaker than typical human-made transmissions. Imagine trying to detect a whisper from billions of miles away while someone next door is shouting through a megaphone. It's incredibly difficult.
Yeah, I can definitely see how that would be a problem, like listening for a pin drop in a factory.
Exactly. This makes radio astronomy highly vulnerable to radio frequency interference, or RFI.
And the sources suggest this threat is actually growing. It's getting worse.
It is, significantly. The proliferation of broadband digital modulation, ultra-wideband devices, spread spectrum techniques, and just the sheer number of unlicensed wireless devices like smartphones, laptops operating near telescopes, it's all contributing to increased RFI, a constant barrage of noise.
So even if a frequency band is allocated to radio astronomy on paper, it's not fully protected in reality.
Precisely. Mere allocation isn't enough. Specific protections are required, sometimes really strict regulations, like footnotes in the International Radio Regulations that prohibit any emissions in passive bands. International and national efforts, like those coordinated by groups like IUCAF, are constantly working to protect these critical bands, but it's an uphill battle.
What happens when RFI actually gets into a radio telescope? How does it mess up the data, practically speaking?
Well, it adds noise, plain and simple. It degrades the quality of the observations. The sources note that just a 10% increase in noise due to RFI can mean a 20% loss of observing time, basically. You have to stare at the source for much longer to get the same quality of information.
20% longer? That's significant.
It is. And in severe cases, strong interference can even damage or saturate the sensitive receivers, just overload them completely.
That sounds serious. Is there like a threshold for what's considered detrimental interference?
Yes. The sources define it based on receiver output fluctuation. Basically, levels causing a 10% increase in the noise fluctuations are considered detrimental. The ITUR has set limits on acceptable loss of observing time. No more than 5% total loss from all interference sources combined, and crucially, no more than 2% from any single interference source. That shows you just how sensitive the science is.
Wow, only 2% from one source.
Oh,
Okay, and interference isn't just from people transmitting in the protected bands, is it? It can leak in.
no, and this is a major challenge. Interference can come from transmissions outside the allocated bands through several mechanisms. One is simple bandage interference, where a transmission spectrum doesn't cut off cleanly and leaks or spills over into the adjacent radio astronomy band.
Like the sound from one radio station bleeding into another on your car radio dial?
A bit like that, yeah, but often from powerful transmitters operating right next door to the protected band. Then there's something called intermodulation, which is really tricky.
Intermodulation, what's that?
If two or more strong signals hit nonlinear components inside the receiver, tiny imperfections in the electronics, they can actually mix together and create new frequencies that fall right inside the radio astronomy band, even if the original signals were way outside it.
Whoa, so you get a new unwanted signal generated right there in the telescope's own electronics from outside signals mixing.
Exactly, it's insidious. Another problem is harmonic radiation unintentional emissions at integer multiples of the transmitter's fundamental frequency. So a transmission at, say, 10 gigahertz might have a weaker unintended emission at 20 gigahertz or 30 gigahertz that could fall into a protected band. The sources mention the potential second harmonic from broadcasting satellites impacting the 23.6 to 24.0 gigahertz passive band used for water vapor studies.
Okay, lots of ways for unwanted signals to creep in. Can you give us some real-world examples of interference that have been particularly troublesome?
Oh, definitely. The transition from analog to digital television is one. Digital signals tend to fill the spectrum more completely than analog signals did. Figure 6.3 in the source shows this difference quite clearly. This means you need really substantial separation distances between digital TV stations and radio observatories, as shown in Figure 6.6, hundreds of kilometers sometimes.
Digital TV causing issues, and satellites, you mentioned them earlier.
Satellites are a huge constant challenge. Geostationary satellites, the ones that stay in one spot in the sky, constantly illuminate large areas of the Earth, and their side lobes sort of stray signals can easily hit telescopes. And having multiple satellites in view is obviously a problem. Plus, the new large constellations of low Earth orbit, or LEO satellites, they're presenting entirely new and evolving challenges because they move across the sky.
Satellites seem like a particularly tough nut to crack.
They really are. A significant case study highlighted in the sources involved interference from the Iridium mobile satellite service system. This was in the 1613.8 millihertz band, which is near an important band for studying hydroxyl molecules.
Okay, what happened there?
What was striking here is that the interference wasn't from the receiver on Earth being overloaded. It was actually caused by seventh-order intermodulation products generated on the satellite itself.
Generated on the satellite and beaming down.
Yes, mixing happening up there. Measurements showed a median of 76% three-quarters of the observing bandwidth in that range was contaminated by these unwanted signals. They exceeded the official ITUR protection thresholds by over 20 dP.
20 decibels. Translate that for me.
That's a factor of 100 in power. The interference was literally 100 times stronger than the acceptable limit. Figure 6.do in the source shows a spectrogram, and you can just see these intense vertical lines completely dominating the band. It's brutal.
Wow.
And high-power radar signals, even from things like, modern vehicular radars, can also be a problem due to their focused beams potentially saturating or even damaging receivers if they point directly at the telescope.
That's, a constant battle against noise and unwanted signals. So how do astronomers fight back against this? What can they actually do?
Well, they employ various mitigation techniques. Signal processing is absolutely crucial. Modern observatories digitize the incoming signals almost immediately and then use sophisticated digital filtering techniques like FIR or polyphase filters. These can create incredibly sharp cutoffs at the edges of the protected bands, much sharper than old analog filters could manage.
So like digital walls around the protected frequency.
Exactly. Also, ensuring the receiver has enough headroom, meaning it stays linear and doesn't get overloaded, even when strong signals are present just outside the desired band. That's vital to prevent things like intermodulation.
Okay, better filters, more robust receivers. What else?
They also use interference rejection algorithms. These are complex software routines that analyze the data, identify components that look like RFI. Often, RFI has distinct characteristics compared to cosmic signals, like being narrowband or periodic, and then try to remove or flag those components. Techniques include excision, just cutting out the bad data, flagging it so it's ignored, and more advanced adaptive filtering.
Software trying to clean up the mess.
Essentially, yes. And finally, careful planning and coordination with active service users are essential. Sometimes this means time-sharing or frequency-sharing agreements, especially if astronomers need to observe outside the officially allocated passive bands for a specific scientific reason.
It sounds like a monumental effort just to keep the airwaves clear enough to hear anything faint. Are there special places designated to help with this, like protected zones?
Yes, exactly. This leads to the concept of radio quiet zones, or RQZs. An RQZ is a specific geographic area where spectrum management is intentionally modified, tightened up, basically to reduce or avoid interference to radio observatories located within that zone.
How do they actually establish and protect a quiet zone like that?
It's a mix of strategies. You have regulatory controls on who can transmit what and at what power level within the zone. Technical measures, like requiring shielding on equipment. And crucially, leveraging geographic advantages.
Geography, how does that help?
Well, locating observatories far from cities and populated areas is the obvious first step. But natural terrain can also provide significant shielding. Placing a telescope deep in a valley surrounded by mountains can physically block many ground-based signals. And surprisingly, even dense forests, especially coniferous trees, can help absorb some signals, particularly at higher frequencies, thanks to their moisture content.
So, a telescope hiding in a mountain valley surrounded by pine trees could be surprisingly quiet. That's a neat detail.
It really can help. RQZs can have different structures, too. Sometimes there's an absolute exclusion zone right around the telescope where practically no transmissions are permitted, combined with outer zones where transmission levels are strictly limited and coordinated.
But even in a designated quiet zone, you must still have challenges, right? It can't be perfectly silent.
Oh, absolutely. Interference isn't only from fixed towers. Mobile sources are a big problem aircraft, for instance. From cruising altitude, an airplane can be visible radio-wise up to 400 kilometers away due to the radio horizon, potentially causing interference.
400 kilometers.
And then there are unintentional radiators. These are everywhere, things not designed to transmit radio waves, but which emit radio noise anyway as a byproduct of their operation. Think vehicle electronics, industrial machinery, computers, and yes, even microwave ovens.
So my kitchen microwave could potentially be interfering with a multi-million-dollar radio telescope nearby?
Potentially, yes,
Yeah.
though the range is thankfully limited compared to a transmitter tower. But collectively, all these unintentional radiators create a pervasive background of low-level RFI, even within supposedly protected zones. There are established examples, like the National Radio Quiet Zone around the Green Bank Observatory in West Virginia. It has very specific restrictions on radio transmissions and even controls on new developments that might generate interference.
And these zones need to last, I imagine. You build an expensive telescope there.
Yes, exactly. Establishing an RQZ requires serious long-term planning. You have to consider the economic impacts on the region, and importantly, the zone needs to be adaptable. New technologies emerge all the time, creating new potential sources of RFI that nobody anticipated. So continuous monitoring and enforcement are absolutely essential to keep these zones effective.
Beyond these ground-based quiet zones, the sources also mention special locations for observations. Where else are radio astronomers setting up shop or wanting to?
Well, space itself is ideal for avoiding atmospheric absorption and, of course, a lot of Earth-based RFI. We mentioned space VLBI earlier. Putting antennas in orbit gives you baselines larger than Earth's diameter, leading to even higher resolution imaging.
Right, bigger baselines.
And the L2 Sun-Earth Lagrangian point is another prime location. It's a gravitationally stable point way out, about 1.5 million kilometers from Earth, on the site opposite the Sun. It offers very low thermal noise and natural shielding from Earth's RFI. This is where satellites like COBE, WMAP, and Plan Seek and Key K were positioned for those crucial CMB studies we talked about.
Shielded by location, far out in space. Makes sense. What about the moon? I hear people talk about the far side.
The far side of the moon is often considered the ultimate quiet zone for radio astronomy, especially for very low frequencies, say below 30 megahertz. Down there, at those low frequencies, the Earth is incredibly noisy, radio-wise, and our own ionosphere actually blocks most signals from space from reaching the ground anyway.
So the moon blocks Earth's noise and lets us see low frequencies we can't see from here.
Precisely. The moon's physical bulk provides unparalleled shielding from Earth's radio pollution. It's potentially the quietest place in the inner solar system for radio observations.
And what can you see at those really low frequencies that you can't see elsewhere?
Phenomena only clearly visible there. Things like detailed studies of solar activity, how cosmic rays interact with things, mapping the magnetic fields of our galaxy, and even distant galaxies. and potentially looking back even further in cosmic time, because the light from the very earliest stars and galaxies would be extremely redshifted, possibly due to these very low frequencies. It's a unique, unopened window.
A whole new view of the universe.
Potentially, yes. And back on the ground, of course, there are also special sites chosen for their excellent atmospheric conditions, particularly for high-frequency observations where water vapor is a problem. Places like the high, dry Antarctic Plateau, the South Pole, the ALMA site in Chile at 5,000 meters elevation, or Mauna Kea in Hawaii. High and dry is key.
Okay. So far, we've focused mostly on passive listening radio astronomy, but the sources also cover active sensing. What's that about? Radar.
Exactly. That's radar astronomy. Unlike radio astronomy, it's an active service. You deliberately transmit a powerful radio signal towards an object and then listen for the echo bouncing back.
So sending out a ping and catching the return, like sonar, but with radio waves.
Pretty much. Because you're dealing with a signal that has to travel out and then back, the power loss increases dramatically with distance. It falls off as distance to the fourth power, actually. This limits radar astronomy to objects relatively close to us, primarily within our solar neighborhood. But within that range, it's incredibly powerful.
What are its key applications, then, if it's limited to nearby objects?
Well, it's the only method capable of detecting and accurately tracking small-scale space debris stuff less than 1 centimeter in size. That's crucial for satellite safety.
Wow, tracking tiny bits of junk.
Yep. It's also used to image spacecraft in orbit, study near-Earth objects like asteroids and comets, figuring out their size, shape, spin, and trajectory hazards. And it's used to map the surfaces of nearby planets and moons that might be hidden by thick atmospheres like Venus or just hard to see clearly otherwise, like Mercury, Saturn's moon Titan, or Eggedius. It's even been used to study Saturn's rings in detail.
That sounds really essential for planetary science and, space safety. Are there many of these radar astronomy sites?
No. Actually, there are only a limited number of active sites globally with the power needed. Historically, the most famous was the giant Arecibo Observatory in Puerto Rico, which tragically collapsed. There's one in California, one in Crimea, and these powerful antennas are often shared, used for passive radio astronomy or deep space communications when they're not transmitting for radar.
Okay. Limited but powerful. And finally, the topic that always captures a lot of public imagination. The search for extraterrestrial intelligence SETI. How does that tie into this whole radio spectrum picture?
Well, SETI's goal is distinct from natural radio astronomy. It's specifically looking for artificial, coherent signals that look engineered, basically that might indicate intelligent life elsewhere. It's important to note, as the sources do, that SETI is a scientific endeavor. It's quite separate from ufology, reports of unidentified flying objects, for which there's currently no accepted scientific evidence.
Right. So listening for deliberately engineered signals, not just tracking unexplained lights or phenomena.
Precisely. The modern history really dates back to Project Ozma in 1960, led by Frank Drake at Green Bank. He famously chose to search near that 1420 megahertz hydrogen line we talked about. He called it the water hole frequency.
The water hole? Why?
Because water, H, contains hydrogen, H, and hydroxyl OH, and these components emit near the hydrogen line. Since water is fundamental to life as we know it, Drake reasoned that intelligent civilizations might choose this cosmically significant, relatively quiet spot in the spectrum to deliberately signal. It was a logical place to start looking. Later efforts included NASA's Microwave Observing Program and Project Phoenix.
So what does SETI look like today? Are we still listening at the water hole?
They listen there and across much wider frequency ranges now. Modern projects include facilities like the Allen Telescope Array, or ATA. It's designed for multi-beaming, looking at many spots on the sky at once and searching across a very wide range of frequencies, from about 0.5 to 11.4 gigahertz, very efficiently.
Has it found anything?
The ATA has sifted through millions and millions of potential signals, but to date, every single one that looked interesting has ultimately been identified as Earth-based RFI, our own transmissions, satellite signals, that kind of thing.
So RFI is a massive problem for SETI too, maybe even more so.
Oh, it's arguably the biggest challenge for radio SETI. From SETI's perspective, all human-made transmissions are potential RFI that could completely mask a faint, genuine extraterrestrial signal. The increasing density and complexity of the radio spectrum, especially with all the growing satellite constellations, makes searching harder and harder. It's particularly difficult to search in parts of the sky near the geostationary satellite belt, which is just packed with signals.
Are they only searching for radio signals, though, or are there other approaches?
No, the field is definitely broadening. There's optical SETI, which searches for brief, powerful pulses of laser light that might be used for communication. And there's the wider search for technosignatures.
Technosignatures.
Yeah, looking for any indirect evidence of advanced technology. This could range from detecting huge artificial structures, like Dyson spheres built around stars to capture their energy, or maybe finding industrial pollution in the atmospheres of exoplanets, detecting city lights on their night sides, or even spotting evidence of asteroid mining on a vast scale.
Wow, searching for cosmic engineering projects, that really expands the potential targets hugely, doesn't it?
It does, but detectability remains a huge challenge for any of these methods. Signals, whether radio or light or atmospheric traces, are likely to be incredibly weak, requiring long observation times. And accounting for Doppler shifts from moving sources adds complexity. The Drake equation tries to estimate the factors involved, but the core problem remains: finding a potentially faint needle in an ever-growing haystack of our own radio noise and astrophysical signals.
We've certainly journeyed a long way here, from mapping our galaxy's structure to searching for cosmic engineers. And that brings us to the final section in the sources, which really delves into the profound implications of actually making contact with an advanced civilization. Heavy stuff.
Yeah, this is obviously highly speculative territory, but the sources do highlight the need to at least consider the significant potential impacts, both good and bad. The analogy often drawn is with historical human cultural encounters, like the Columbian exchange between the Old World and the New World. And sadly, many such encounters led to the destruction or severe disruption of the contacted culture, usually the less technologically advanced one.
So, contact isn't necessarily a guaranteed good thing. Could be risky.
That's certainly a perspective raised in the sources, yes. Theories about alien motivations vary wildly, as you can imagine. Some envision benevolent entities wanting to share knowledge or technology, maybe via radio or sending probes. But even that could potentially lead to a loss of human identity if we became overly dependent or felt inferior.
And the less benevolent possibilities.
Others consider malevolent motives like conquest, although the sources speculate that truly advanced civilizations might have solved resource issues and wouldn't necessarily need to conquer. Perhaps more subtly, there's the theoretical risk of a message itself being dangerous.
A dangerous message. How so?
Well, imagine a message containing dangerous knowledge. Maybe instructions for creating uncontrollable super AI, or blueprints for incredibly potent weapons sent either intentionally as a trap or even unintentionally by a civilization that didn't realize how disruptive it could be for us. Sources suggest biological weapons or viruses are less likely without specific knowledge of human biology, but engineered threats couldn't be totally ruled out.
That's unsettling to think about. What about the idea they might just avoid us altogether?
That's the zoo hypothesis, the idea that maybe one or more advanced civilizations deliberately avoid contact to allow cultures like ours to develop naturally without interference. This connects to the famous Fermi paradox, the apparent contradiction between the high probability of alien life existing somewhere and the complete lack of confirmed evidence or contact so far. Where is everybody? The grabby aliens model is one attempt to explain this paradox. It suggests that if technologically advanced civilizations tend to expand rapidly and visibly, grabby, then our relatively early emergence in cosmic history might mean we simply evolved before any such nearby civilization reached our neighborhood. If they expand slowly or subtly, they could already be out there, or even here, undetected.
And this feeds back into the SETI debate we touched on. Is it actually dangerous to transmit signals ourselves? Messaging extraterrestrial intelligence, or maybe...
Exactly. If potentially grabby or unpredictable aliens are out there, actively transmitting signals makes us much more visible, which some scientists argue is a significant and unnecessary risk. Listening, SETI, might be inherently safer than actively shouting into the cosmos, Treasury. It's a major debate within the community.
Given all these potential risks and the sheer unknown nature of it all, are there any agreed-upon protocols if we do actually detect a credible signal someday?
Yes, there are. Organizations like the International Astronomical Union, IAU, and the International Academy of Astronautics, IAA, have developed a declaration of principles concerning activities following the detection of extraterrestrial intelligence. The core steps are pretty logical. First, verify the signal rigorously. Then, inform other researchers and relevant international bodies. Publish the discovery openly in scientific channels. Notify the ITUR because of the frequency implications. And crucially, agree internationally before sending any response. No single nation or group should reply unilaterally.
No response without international agreement. That sounds sensible, but would it actually hold?
That's the big question. The sources acknowledge there's considerable skepticism about whether these protocols would actually be followed in the heat of the moment. Imagine the intense pressure for immediate public disclosure, potential national security concerns, scientific competition, or just the sheer excitement overriding caution. Vested interests could play a huge role.
Yeah, you can see how that might unfold. It really highlights the immense complexity, scientific, political, cultural, ethical, that would immediately arise even before any actual interaction occurred.
Indeed, it would change everything instantly.
So we've really taken quite a deep dive through this material today. We've explored how radio waves allow us to map the very structure of our own galaxy, understand the universe's origins through the CMB, monitor our own sun to protect critical infrastructure here on Earth.
And how we actively search for both faint cosmic echoes using radar and potentially revolutionary signals of life through SETI. And underpinning all of it, as we've seen, is the absolutely critical and increasingly challenging task of protecting those tiny, quiet slivers of the radio spectrum that are needed for these observations.
It's quite something. The incredibly weak signals from the most distant corners of the universe, or the faint echoes we manage to bounce off our nearby planetary neighbors, are constantly threatened by the ever-increasing noise of our own technological advancement. Protecting those quiet bands isn't just about enabling scientific discovery, is it? It feels like it's about preserving our fundamental ability to hear the universe and potentially answer that profound question. Are we alone?
Which really leaves us, and you listening, with something important to consider. Given the immense value these observations provide, everything from fundamental science to protecting our daily lives and the potentially world-altering implications of detecting other lives, how much do we as a society truly value the quiet frequencies that let us listen to the cosmos and perhaps, just perhaps, find that ultimate answer? How much is that silence worth?